So with our next unit here, what we're actually going to be starting is a different type of calculus. So what we've spent our entire time working on so far is what's called differential calculus, where the focus is on instantaneous rate of change, or how quickly something is changing. And graphically, this is where we were looking at slopes. But now we want to switch over and start talking about what's called integral calculus, where it's not so much how quickly things change that we care about, it's the accumulated change, how much something changes. And this is going to involve areas. Now, please note I say involve. Over the course of this unit, we're going to explore the fact that when we talk about how much something changes, graphically, it's related to area, but it's not exactly the same thing as area. Just kind of keep that in the back of your mind for the next few days as we go through this unit. So this section, I'm going to take everything graphically here, just because it's easier to work graphically to start with this. The idea of this is if, let's take the example of a train is moving at a steady rate of 70 miles per hour from 6 a.m. to 8 a.m. And we want to find the total distance the train travels. Well, you're like, well, 70 miles per hour for 2 hours, that's 140 miles. But I want to kind of explore graphically what did that find for us. And so if I graph the velocity of 70 miles per hour right here, and we'll pretend that's a completely perfect horizontal line. Whoops, sorry about that. And we say, well, it's from 6 a.m. to 8 a.m. So here's 6 a.m., here's 8 a.m. What I've got is a rectangle here. And in this rectangle, its height is the 70 miles per hour. And then its width I found by subtracting 8 minus 6 to get the 2 hours. So then when I'm saying I'm doing 70 miles per hour times 2 hours to get the 140 miles, what I actually found is that's the area between my function, the 70 mile per hour function, and the x-axis. And this is an important thing for us here. So this is big for us. We're going to be spending a lot of time in this, while talking about integral calculus into third quarter, where we're finding these areas between a function and the x-axis. But while we deal with things that are constant, or if I have a constant acceleration, so a constant rate or a constant second derivative, where it gets complicated is those aren't really realistic. So if I wanted a more realistic example, if I stick with the train doesn't move at a constant rate. It has to speed up, it slows down, it stops, and based on what the track is doing. Are we going uphill, downhill? Are we going around a turn? How sharp is the turn? Is the turn, as we're turning, do we have to go uphill or downhill? Where are the stations? Because trains have to stop for people to get on and off. Otherwise, it gets a lot more dangerous. So a more realistic graph of my function would be something that would look like this, where I've got speeding up, slowing down, stopping. And if I wanted to know a total distance to find then, what I'm trying to figure out is, well, how would I find the area between this function and the x-axis? It's not going to be nice rectangles. So the way we approach this is we say, well, we don't have to get a perfect distance. what if I just say, let's estimate the distance? And to do that, the idea we use is we break this up into simpler regions and say, well, what if I find these areas separately and then add those areas up? So, and that's actually a concept you've done, whoops, sorry about that, before with finding areas back in grade school where they say if you have a complex shape and you need to find its area, break it into smaller pieces and find the area of each piece and add them all up. Well, this idea actually has a name. It's called a Riemann sum. So a Riemann sum says, let's break the area into smaller, simpler shapes whose areas we can find. Rectangles are awesome. Triangles, trapezoids, etc. What's a little different for us is we don't get control of the height, we can only control the width. And this is because of which variables we have control of. So if I go back to my example here, I can't control how tall my shapes are because the height is being determined by my function, which is a dependent variable. But I can control the widths because the width is determined by x, which is my independent function, and we maintain control on. So I could say, from 0 to 2 is going to be one of my shapes. From 2 to 4 is another. From 4 to 6. From 6 to 8. From 8 to 10. And say, okay, those are those areas. But then if I say, well, I could make them rectangles. Here's a rectangle. Here's one. Well, those aren't going to be perfect estimates, but it gives me a reasonable estimate because some of the rectangles are too big, some of them are too small, but they average out, and I should get something that's reasonably close to the exact value. For our course, we're going to be focused on rectangles, on trapezoids, and in BC, we use what are called semi-paraboloids. And when we get to those in BC, we'll talk about them. One strange thing on the AP exam, if they use the phrase Riemann sum, they specifically are referring to rectangles. Whereas more broadly in mathematics, a Riemann sum just means that idea, break a shape into simpler shapes, find the simpler areas and add them up. But again, we'll practice all of that.